This is problem 13164 on page 903. Two identical billiard balls can move freely on a horizontal table. Ball A has a velocity v naught as shown and hits ball B, which is at rest, at a point C defined by theta equals 45 degrees. Knowing that the coefficient of restitution between the two balls is 80%, and assuming no friction, determine the velocity of each ball after impact. All right, so let's sketch the system. We've got a ball moving this way. It's called A, and it has velocity v naught. I may be sorry I chose this one. I'm not sure if we'll end up with numbers or not. So eventually A moves to this position where it impacts with ball B along the line defined by a 45-degree angle. V naught down. In fact, let's make it V naught of A. Coefficient of restitution, E equals 0.8, is all that we know. Now we're assuming there's no friction. And we're supposed to determine the velocity of each ball after impact. VA, VB, we'll just call them prime after impact. Okay. Yeah, I don't think we'll end up with a number but an equation. Or at least the velocities in terms of the initial velocity of A. With oblique impact like this, you conserve conserve entropy. That's wrong on two levels, wrong class, and it's not true. Entropy is always created. But anyway, so you would conserve momentum along this line. Okay. The reason they say no friction is twofold. First of all, we're assuming there's no frictional forces that are significant between the felt and the balls, for example. More importantly, there's no friction in order to transfer any force in this direction. Does that make sense? So really what we need to do is set up an x, y axis so that basically, since there is no force in this direction, the momentum in the y direction will be unaffected because the only force on A from B is force along this line. Does that make sense? So that's the approach we're going to take. You could set up x, y any way you want. I happen to draw it this way. It doesn't really matter. So what I'm going to do is realize once A reaches this position, what I really need to do is break up its velocity into two components. So I know red doesn't show up real well, but all I'm going to do is show you that there are two components to the velocity, and they would actually be equal because we've got a 45-degree angle. So could we calculate the velocity of A in the x direction, three subscripts for the velocity, but there it is. So the initial velocity of A before impact along the x-axis, well, it would be some portion of the initial velocity of A. Now let's see, would that technically be the sine or cosine side? I know it doesn't really matter, but let me think about it for a second because I would rather, let's see, so there's the initial velocity of A, and I'm basically breaking it up into vectors like that, right? So I would say the 45-degree angle is right there. And it's probably a little more correct then for me to say that along the x direction, that's the cosine side. So cosine of theta, theta being 45 degrees. And the initial velocity of A along the y direction would be VOA sine theta. Okay? Now, it's the component of velocity along the y direction that will be unaffected because, again, if there's no friction, there can be no force in this direction. The only force can be along this line, and so this is actually the velocity of A in the y direction after impact. Okay, it's the same. There's no change in it. How about the x direction? So this is the interesting direction. What happens there? Well, momentum will be conserved in that direction. So what we would write is V naught AX MA, okay? Or just M, well, let me leave an A on there so you'll see why. The mass of A and B are the same. So this is the momentum in the x direction of ball A plus the initial momentum of B in the x direction, well, guess what, that's 0 because it's not moving, equals the momentum of A in the x direction after impact plus the momentum of B in the x direction after impact. Okay. Now the mass of A and B are all the same. That's the reason we can cross off the mass of A in this equation and write that the initial velocity of A in the x direction equals the final velocity of A in the x direction plus the velocity of B in the x direction after impact. Okay? Any questions so far? Okay. So, now notice I have, again, one equation, two unknowns. So the other equation will have to come from the coefficient of restitution. So let's see. The velocity of A in the x direction after impact minus the velocity of B in the x direction after impact divided by the velocity of B initially, let's say, initial B x direction before impact minus the velocity initial A x direction before impact. Obviously this one is 0. With that, we can rearrange and say that negative E V naught A x equals the relative velocity after impact. And of course, we'll just rearrange this, I guess solve for V A prime x, the velocity of A in the x direction after impact. That would be equal to V B x after impact minus E V naught A x. So let's take this and plug it in for V A x prime. Well, better yet. Right there. So now this would be equal to, let's see, VB prime minus EV naught AX plus VB x prime. Guess we'll take this equation, move it over here. Say, let's see, we want VBX prime by itself. So what we'll do is just write V naught AX, that's this piece, plus EV naught AX, that's this piece, equals 2 VBX prime. And so, VBX prime, the velocity of B after impact, is the initial velocity of A in the x direction times 1 plus E divided by 2. E is not the special number E, it's the 80% coefficient of restitution. So, the initial velocity in the x direction is V naught A cos theta, and this would be 1.8 over 2, because the coefficient of restitution is 80%. So there's the velocity of B after impact, in the x direction at least, which, by the way, could B have any velocity in any other direction? No, there's no friction, right? The only way that force can be applied to B is along that line. That's what's interesting about playing pool. If there's not much friction between the balls, you can neglect it, and you've got to get A, or your cue ball, to hit the ball in the right, just the right place, because what you're trying to do is control the angle of that line so it'll go into the pocket, okay? Anyway, so there's VBX prime in terms of the initial velocity of A. Let's go ahead and get the final velocity of A in the x direction. I think they asked for the velocity of both balls after impact. Yeah, velocity of each ball after impact. So let's go ahead and get the velocity of A in the x direction after impact. And for that, we've got an equation here to do it. So let's see, we'll just, well, I guess that's off the screen, isn't it? So let me, let's see, I missed my mark. Oh well. Probably the easiest thing to do is to just erase some of this and continue, because we've got the velocity being the x direction after impact. So VAX prime is VBX prime, well that's just this, V naught A cos theta times 1.8 over 2, that's this term, minus E, I'll go ahead and substitute 0.8, V naught AX. Well, V naught AX is V naught A cos theta. And so let's see, all we need to do is, looks like take 0.8 away from 1.8 over 2. Well, 1.8 over 2 is just 0.9, isn't it? So we can just write that. And so 0.8 away from 0.9 would give us 0.1. So 0.1 V naught A cos theta would be our result. And I guess we could make that substitution here as well. This would be 0.9 as well. Okay. So it's interesting that, well, I won't say that, it doesn't matter. But that's not all of the velocity of A after impact. In fact, the velocity of A after impact would be the square root of V, let's see, how do I want to say this? VAX prime plus VAY prime. You see what I'm saying? There's going to be some velocity of A in the X and the Y direction after impact. To get the magnitude of that velocity, I'll have to take the square root of the sum of the squares. Okay? So, VAX prime, we've got an expression for it, that's right here, root 0.1 V naught A cos theta, and all of that will have to be squared, plus VAY prime. Well, VAY prime is just V naught A sine theta. Okay. So let's see, it may be helpful to also know the direction. If we want to know something about the velocity, they ask for the velocity. Velocity is both magnitude and direction. So let's get direction before we get too far ahead of ourselves. Well, I guess we can continue with this. So root, if we square this, we're going to have 0.1 squared. We could pull out the V naught A. Let's just do that. It's pretty obvious we're going to have a V naught A squared, and that will just come out. Root 0.1 squared cos theta squared plus sine theta squared. Okay. And of course we know that the cosine of 45 degrees and the sine of 45 degrees are the same thing. Right? So we could write V naught A root 0.1 squared plus 1 quantity, and you know that the cosine of 45 degrees is just 1 over root 2, right? So 1 over root 2. All I've done is I've factored out cosine and sine, not because you can normally do that, but because they're equal to each other in this particular case. Right? These are both 1 over root 2. So I just factored that out, and this is what we're left with. So go ahead and calculate it if you would. Just tell me what all this is. So 0.1 squared would be what, 0.01? Am I thinking right? So 1.01 over the square root of 2 and then the square root of that result is going to be some probably odd, irrational number, but just give me 4 decimal places or so. That should be enough.
0.845.
0.845, so maybe one more decimal?
One.
Okay. V naught A. So turns out that A ends up with most of the velocity after impact, 84.5% of it. And that's not really surprising because X hardly moves. What does that mean? Well, that means if the ball glances off at some other angle, it could go into a pocket. And you scratch the cue ball, which is not good. That means, what does that mean? I guess it depends on how you play. We always play, you have to take the ball back out.
The book has this equation, or I guess it's more like a principle, that VA in the T direction, which is your Y direction, is conserved. VA Y equals, or VA initial Y equals VA final.
Right, that's what I've said right here.
Okay.
This is amazing. Yeah, no, you're fine. That's a good point. So the point is there are no forces in this direction, right? There's no friction. Therefore, there's no way the momentum of the ball in that direction can be changed. Only the momentum in the direction of forces. Yeah, that's right. That's correct. So let's see. The other thing we want to know is, well, which way is the cue ball going? Because now our ball that we've hit, even if we've hit it in the right direction, it's slowly rolling to the pocket. It'll probably go in. But which way will the ball go? Well, let's find out. So looking at this equation, we can pick off VAX prime, VAY prime, and say that the tangent of the angle, let's call it alpha, okay, the tangent of the angle alpha, which will be the angle of the cue ball after impact, would be equal to, well, it's just y over x, isn't it? So we just need y, v naught a sine theta, over x, 0.1 v naught a cosine theta. Of course, in this particular case, sine and cosine are the same, so we simply get 1 over 0.1. So what is the angle alpha then? You take the inverse tangent of 1 over 0.1, or the inverse tangent of 10. How much?
84 degrees.
84 degrees, thank you. What does that mean? 84 degrees from what? Well, 84 degrees from this line, right? So the ball continues off something like that, where this angle here would be alpha. Hopefully striking a bumper and safely staying on the table. Okay, any questions? So we've got the final velocity of A. Oh, you know what? I forgot the velocity of B. No, I didn't. Here it is. That's the only velocity it would have, and it would only be in the x direction. I guess we could simplify this a little bit. What happens when you take 0.9 over root 2?
.636.
636 V naught A. Well, you know what I want to do now, right? Since I teach thermo, I want to see if energy is conserved, or did I make a mistake? Well, I know energy is certainly conserved, but in a sense it's not, because some of the mechanical energy is transformed into thermal energy. So let's find out. I mean, I could have made a mistake. I've done a whole bunch of math here, and maybe I've got it wrong. Let's find out. Let's calculate the energy before impact. So let's just call it E naught. How's that? It would all be in A, so it would be 1/2 the mass of A times the initial velocity of A squared. And that's as deep as we can go, because we don't know the mass of A, and we don't know the velocity of A initially. Let's continue, though, and ask about the energy in state 1, or the energy in state prime, the energy after impact. Well, that would be 1/2 mass of A, and we want the velocity of A after impact, so that would be 0.636 V naught A. Well, we'll have to square the whole thing. There we go. Plus 1/2 mass of B times 0.8451 V naught A squared. Now the mass of A and mass of B are the same, so I can just make that substitution. So I hope that basically 0.636 squared plus 0.8451 squared in the square root doesn't come out more than 1, because if it does, I've made a mistake somewhere. Well, let's find out. So take 0.636 squared, add to it 0.841 or 8451 squared, and what do we get?
1.12.
Uh-oh. Either I've made a mistake somewhere, or we found a way to make perpetual motion machines a reality. I've made a mistake somewhere, I don't know where. The analysis along the way, the idea is correct, that momentum of A will be unaffected in the y direction and only affected in the x direction. So I'll try to look through it when I post the video and put something in the comments about where the mistake is. Okay? Any questions?
Well, and I'm sure in a real case, some of the energy's not, I mean, it's lost in the friction.
It's not necessarily lost in the friction. There is no friction, at least in this problem. And this number should be less than 1. Had I not made a mistake somewhere, this number would be less than 1. Okay? So, where is the energy lost? Well, when those balls come together, they're going to compress one another to some extent, and then they're going to rebound. Well, the force versus deflection characteristics of the ball will be different as it's being compressed than when it's reconstituting or when it's expanding. And that's where the energy loss actually occurs. Okay? Any questions about all that? Sorry, I made a mistake somewhere. I don't know where it is. I'll find it later.